Hello, I am Mexams, and in this video, I will take you through the differential of trigonometric functions, logarithm functions, and exponential functions. Okay, so let's start. So, trigonometric functions, how do you differentiate trig functions? Okay, the basic definition that we are supposed to have in mind is that whenever you differentiate sine x, you get cos x, and whenever you differentiate cos x, you get minus sine x. Okay, so you just put it in mind when if y equals sine x, then the derivative of y, which is the derivative of sine s, is what? Cos s. And if y equals what? Cos s, then the derivative of this cos s is equal to minus sine x. Okay, you actually prove them later, but keep them in mind, because we need them to solve some exam practice questions. After that, we just take our time and go through them step by step and prove all of these. Okay, now note, if y equals sine u, where u is also u of x, that means u is a function of x, then we use chain rule. Okay, chain rule in the sense that you first differentiate the function sine and you get what? Cos. Then you differentiate the u. So this will be like, let's go through it like that is it. Dy dx will be equal to dy du times du dx, and in this case dy dx will be equal to cos of u times du dx, where we have sine y equals sine u. This will be the differential. Okay, so it will be cos of whatever u that you have, then times du dx. Okay, the same applies to cos u, where u equals u of x. So if you have cos, that is the cos of a certain function that is another function of x, then you know how to go about it using the chain rule. Okay, so let's go through some basic trig identities and see other trig identities. Okay, given that y equals tan x, find dy dx. How do I differentiate this? Okay, but we know that we can rewrite tan x in terms of sine and cos, right? So if that is the case, if y equals tan x, then we know that tan x is equal to sine x over cos s, right? Then from our previous knowledge on quotient rule, if you have y equals u over v, where u and v are both functions of x, then dy dx would actually be equal to what? This v times the differential of the top one, the numerator, minus this u times the differential of the denominator, all over what? V squared. So let's see. This is how you go about it. This v times the differential of u, which is the u, minus this u times the differential of v, which is the v. So it becomes v du minus u dv all over v squared. Mind you, this only happens when both u and v are functions of independent variable, that is the x. Okay, now let's see how you go about this. So what will be our v and what will be our u? Our u will be what? Sine x, and our v will be cos x. So du will give me what? Cos, and dv will give me what? Minus sine. Okay, so let's go through it. It becomes v, which is cos s, times the differential of the u, which is cos s again, right? Minus this sine x, that is the u, this is the u, times the v, where the v is what? The differential of cos s, and that is minus sine x. When I simplify the top here, I'll get sine cos squared s plus sine squared s. I hope you can see that. Okay, this time that is cos squared s, this time that is what? Sine squared x, but the minus will multiply minus and I'll get plus. Okay, now from our basic trig identity, you know that sine squared s plus cos squared s is what? 1. Okay, it becomes 1 over cos squared s, and this can be written as what? 1 over cos s all squared. Okay, now what is 1 over cos s? Is sec s. It becomes sec squared s. Okay, so it means that whenever I differentiate tan x, I'll get a sec squared x. Keep it in mind. All right, given that y equals sec s, find the differential of this y. Okay, find dy dx. So if I have y equals sec s, how do I differentiate sec s? Okay, all right, I know that sec s is the same as 1 over cos s. So if I want to differentiate this, then I have to use quotient rule. Okay, and the quotient rule is saying that you differentiate this one, then multiply the down one by it, and that becomes cos s times 0, because 1 in terms of x, the differential of that will give me 0. And minus this one times the differential of this, which is minus sine x, all over the v squared, the down one squared. Okay, so it becomes this 0, this times that will give me 0, so it becomes this times this, which will give me plus, so it becomes sine x over what? Cos s times cos s, that is cos squared s, right? And now this will give me 1 over cos s times sine s over cos s. Okay, now this is equal to what? 1 over cos s is what? Sec s. It is here. And sine s over cos s from the previous example that we did is what? Tan x. So it becomes sec s tan x. So whenever you differentiate sec s, you get sec s tan x. Okay. If you can't put it in mind, or if you can't keep it in your mind, you can always remember these um steps and then use it whenever you are being asked to differentiate sec s or something like that. But mind you, if you have sec of u where u is a function of x, you know how to go about it, right? And if it is in terms of tan, then you know how to also go about it. Okay, I mean tan u where u is also a function of x, you use what we know as the chain rule. Okay, so now given that y equals cot s, find the y dx. Okay, how do I go about this one? All right, so cot s is what? You know it's cos s over sine x. So I use quotient rule here. I hope you understand the quotient rule. So let's quote it from here, just straight away like that. The y dx will be what? Sine x times the differential of this, that will give me minus sine s. Then cos s times the differential of this, that will give me cos s. And then I simplify the top, I'll get negative sine squared s minus cos squared s over sine squared s. This will give me negative out, sine squared s plus cos squared s all over sine squared s. Sine squared s plus cos squared s is what? 1. So I get negative 1 over that. And this is the same as negative of 1 over sine s all squared. I hope this is okay. This is from simple computation and simple fractions. Okay. Alright, this 1 over sine s we know is what? Cosec s. So this becomes minus cosec squared s. Okay. So know how these things are related. Cot s is always, or cotangent of x is always related to what? Cosecant of what? X. Okay. Alright, let's continue. So if I have cos x, cosec s, or cosecant of x, how do I differentiate it? Okay. Now, you know that the cosecant of x, or cosec s to be precise, is given as 1 over sine x. Okay. Now, if I differentiate this using quotient rule, I get sine x times 0 minus 1 times cos s all over sine squared s using the quotient rule. Okay. Now, if I simplify the top, what do I get? 0 minus cos s over sine squared s. Alright, and this will give me negative 1 over sine x times cos s over sine s. I hope this is okay. Okay. Now, what is 1 over sine s? Is what? Cosec s. What is this? Cos s over sine s is what? Cotangent of s, that is cot s. And this will give me minus cosec s cot s. So know that whenever you differentiate tan x, you get sec squared s. Whenever you differentiate sec s, you get sec s tan x. Whenever you differentiate cot s, you get what? Minus cosec squared s. Whenever you differentiate cosec x, you get what? Minus cosec s cot s. Know how they are related. But if you have a function or for another function, or if you see a chain rule, then apply the chain rule. Okay, so let's quickly walk through some examples, and then you know how to solve questions when these questions or these type of questions comes. Okay, so I have differentiate the function y equals sec squared 2 of x. All right, sorry, sec squared of 2x. Sorry. Now this is not just a normal x, this is just 2x, so it means it's a function of x. Okay, so I use chain rule here. Now note, apply chain rule to trigonometric functions where applicable. Okay, so here is not just sec x, it's sec squared x, and sec squared of 2x can be written as what? Sec of 2x all squared. So this is like a certain w squared, then in the w we have another 2x, which is also u. Okay, so you know there's a chain rule within another chain rule here. Okay, so if I differentiate just this, looking at the power aspect, it becomes what 2 will come in front times sec 2s, then the 2 reduced to 1. Okay, that is the chain rule. Okay, now you know. So it become 2 times sec 2x. Okay, then we differentiate the sec 2x itself and become sec of 2s tan of 2s, then times the differential of this one. I'm taking it again. Okay, I said using the chain rule from the power chain rule that we know, this will come in front and multiply like a normal polynomial differential, and it will reduce by 1, and we get 2 times sec 2s. That will be okay. Now, since this is a chain rule, we differentiate the bracket here. And differentiating this sec 2s, when you differentiate sec, what will you get? Sec tan. You get sec tan. So it becomes sec of whatever that is here, then tan of whatever that is here. Then we look at it and differentiate whatever that is here again with respect to x, if it is a function of x. So this is what I'm trying to say. When you differentiate this, looking at it from the normal polynomial rule that we know, becomes what? 2 times sec 2s all to the power 2 minus 1. That will give me 2 times sec 2s. Then we differentiate this bracket here, and that will be giving me what? Sec 2s tan 2x. Okay, because when you differentiate sec s, you get what? Sec s tan x. It means whenever you differentiate sec, you get sec tan. It means it will be sec of whatever that is here, then tan of whatever that is here, then multiplied by the differential of this. So the normal one that we were doing, it was actually sec of x tan of x times the differential of x, which is 1, and that's why it was silent like that. In terms where, or in cases where this is not just x, you differentiate the bracket whatever that is here as well, and that will give me 2. So in simplifying, I get what? 4, then sec 2s times sec 2s. This is a bracket here. If I remove the bracket, this can multiply, and I'll get what? Sec squared of 2x, then times tan 2x. Okay, so this becomes 4. This 2 multiply this 2, so I get what? 4 sec squared 2x tan 2x. So this is the differential of this. Okay, I hope this is clear, right? Let's continue. Differentiate the function y equals s cos 2s. Okay, now seeing s, then cos s here, cos 2s, it means I have what? A product rule to deal with. Okay, so from the product rule, s cos 2s, if I have y equals s cos 2s, we use the product rule in solving this type of question. Okay, so from the product rule, what do? We said you keep the second one, you differentiate the first term. Okay, and that becomes what? 1 times cos 2s, and that becomes cos 2s plus, and I have this, I'll keep this x and I differentiate only this. If you remember from our first basic definition, we said that if you have cos x and differentiate, you get what? Minus minus sin x. But if it is this function here is in terms of x, then you have to differentiate it again. So I'll differentiate cos, I'll get minus sine of 2s, then I differentiate this 2s, I'll get 2. So it becomes x, like from the product we keep this, differentiate this, x times in the bracket minus the minus sine 2x will affect this 2. So minus, then this 2, the differential of 2x, I'll get what? 2. Become minus 2 sine 2s. Simplifying, I'll get cos 2s minus 2s sine 2s. Okay, so if you know how to, you can go ahead and use your trigonometric identities and then solve or do whatever you want to do, but this is how the differential will be. Okay, I hope this is clear, right? So now, once we are cool with derivatives of trigonometric functions, let's go through and see logarithmic functions and know how to go about it. So logarithm functions. Okay, so if I want to differentiate logarithmic functions, what do? You need to know this definition. This will help us differentiate every logarithmic function. Now, if I have y equals ln of x, then the differential of this is equal to 1 over x. I'm taking it again. If I have y equals ln of x, then the differential of this y is actually equal to 1 over x. Now, in a case where I have ln of u, where u is also a function of x, then how do I go about it? then dy dx is actually equal to du dx, okay, times 1 over u. So if here is, let's say, a function of x, then I'll use the definition of len and write 1 over whatever that is here times the differential of whatever that is here, okay. All right, different base. When the base is not, I forgot to write this, but you should know that the len of every function is actually the logarithm of that function to the base e, okay. When I have the base e, then I'm dealing with len. That is why we don't write the base. Now if I have a different base, then we can use the change of base here to the base e, that is the len, and that will help us, okay. Now if I have y equals log of x base a, then we know that y can be rewritten as what, len of x over len of a, which is the change of base from base a to base e, which is the len of the function, okay. Now dy ds will actually be equal to what? Then I differentiate, because len of a will give me what? A constant. Len of a, where the a, always this base is a number, so len of a will be a number. So it will be like, I'm differentiating just this, so it's like 1 over len a times this, where the 1 over len a becomes a constant. Where from our basic definitions in derivatives, we know that if we have a constant times a function, then the derivative of the function will be just the constant times the derivative of that function, okay. So here the len a is like a constant, so this become the differential of the top one, that is the differential of this, will give me what? 1 over x. Differential of len x is what? 1 over x, and that will give me over len a, because len a is a constant. So simplifying, I'll get 1 over x len a, and this happens when you have just x to be the function, logarithm of just x. What if the logarithm is with respect to another function u, which is a u of x? Then what will happen? Okay, then this will actually be du dx times 1 over u len a. So it just becomes, here will just be u len a, then multiply everything by du dx, okay. So you differentiate whatever that is here, multiply it by 1 over u len a, okay. All right, so let's continue. So you don't need to, chew this in mind, or just keep this in your mind, that whenever I differentiate len u, I'm sorry, logarithm of u with base a, I'll get this. No, know how to go about it. Know this definition first. After knowing the definition, you can apply it using the change of base to a logarithm, and then that would also help, okay. Now differentiate the function y equals x to the power 4 ln x, okay. So now we use product rule here. Like we said, you first keep the first one, differentiate this one, and keeping this, you keep the second one ln x, differentiate the first one, keeping that, I get what? 4x to the power 3 times ln x plus, then I keep this one, I differentiate the ln x, I differentiate ln x from the definition, you get what? 1 over x, okay. So you count that. Now continue simplification, and you get 4x cubed ln x plus s cubed. Now I can factor s cubed out, and I'll get 4 ln x plus 1, okay. I hope this is okay. All right, let's continue. Now if I have the function, this is more complex one. Differentiate the function y equals len of the bracket sec s plus tan x. Now mind you, here we have a u here, okay. And from the basic definition that we know from polynomial, addition of polynomials, when you are differentiating, you say differentiate this one plus this, the differential of this one, right? So when you want to differentiate something like this, you just differentiate them term wise, okay. All right, so from the definition, we know that use chain rule, u equals what? Sec s plus tan s. Then the du dx, because here it's not just x, so du dx will give me what? Sec s tan x, because we said from the basic definitions that we know from differentiation or derivatives, if you have addition of functions, we said the derivative will be what? The derivative of this plus the derivative of that. And derivative of sec s, from the basic or from the previous definition that we had from sec s, is given as what sec s tan x, okay, and the derivative of tan x will give me what sec squared s, okay. Now dy du is equal to what 1 over u from ln x. If I have ln of u, then dy du will give me what 1 over u, so it becomes 1 over sec x plus tan x. We are doing this in terms of ln of u, okay. I forgot to write that. We're saying that y is equal to ln of u, then it means that the differential of y with respect to u is 1 over u, and that will give me 1 over sec s plus tan x. Now I substitute in this is equal to du dx times 1 over u from the previous definition that we know from logarithm. Okay, I hope you remember that. Sorry, I hope you remember that we said if I have ln of u, then it becomes du dx times 1 over u, right? Okay, so same applies here. Du dx times, so du dx we had was sec s tan x plus s squared x, then 1 over u is what this, all right. So we multiply everything to it, and we can factor some sec s out here, and now get what sec s out tan x plus sec s, because if I factor sec s out from this side, I'll get sec s out, tan s at this place, then plus another sec s at this place, okay. Now this can cancel this, and I'll get what sec s. This is pretty cool, right? So that is the differential of this, okay. So when you are giving differential questions, just take your time, go through it step by step from the definitions that you know, and then you'll be able to differentiate every differential equation or differential question, okay. Now exponential functions. How do I differentiate a function in terms of this? So given that y equals a to the power x, we differentiate it as first find as this, okay. First you find the length of both sides as ln y equals ln of that, and for all that we know that logarithm can do basic things and big magic to us, that to the extent that whatever power that you have, logarithm can bring it down and make the function not a linear function for you to differentiate, okay. So if I have this, then I can differentiate through the whole of this implicitly, okay. So we differentiate it using what implicit differentiation. And so if I differentiate this side, mind you, we said you have to take the length of both sides. If I take the length of both sides, it becomes length of y equals length of a to the power x, and this giving length y equals s length a. Mind you, the length is what a logarithm to the base what e. I hope you understand. Now differentiate this implicitly. I'll get to what the differential of this side will give me what 1 over y times dy dx, and this is equal to the differential of this side. No, the length a is what a constant, so I differentiate just x, I'll get what 1. So this implies that dy dx, making dy dx the subject here, I just multiply or pre-multiply y by on each side, and y will cancel y here, and I'll get y in a. It becomes y in a. Now what is my y? I just come and substitute y in, okay. So we didn't do it here, but in the case of solving a real example, you just have to substitute your y back here, and that becomes a to the power x ln a. That is why most people will tell you that the differential of an exponential function is the same function times the length of the base. I would not urge you to keep that in mind, because in terms where you have this side to be, another function of x, you find yourself in trouble, okay. So but if y equals a to the power u, where u is a function of x, then ln of y will be this, and this will give me that. So when I differentiate this, okay, saying that ln y is equal to u ln a, then the differential of both sides will give me 1 over y. Implicit, when you differentiate ln of something, you get 1 over that, but since here is y, you just multiply dy ds to it, and becomes 1 over y dy ds equals the differential of this u ln a, okay, and that becomes dy ds is equal to what y du dx ln a. How do this? Okay, so differentiate the function e to the power x. This function is very, very important to us. That is why we started with it. Okay, e to the power x. How do I differentiate this? Okay, so treating this, we let our y be equal to that, and then y, we said you take the length of both sides. Then y is equal to what? Length of e to the power x, and this will give me what? Length of y equals length of e. If you know this carefully, if you can note this carefully, then you know that logarithm to the base e is always length. So it means this is the same as logarithm of e to the base e. That'll give me 1, but we don't want to go there yet. Let's pass through what we know and then use it to solve this. Differentiating both sides implicitly, through this equation implicitly, how do I get? I get the differential of that this side will give me 1 over y dy dx from implicit differentiation, and this is equal to differential of x. Here ln e is what? A constant, so you just differentiate s and I'll get what? 1 ln a. And this implies that I have dy dx equals what? Y ln a. But mind you, ln e is what? 1, like I said from here. So we can dy dx equals e to the power x. So it means that whenever you differentiate this function e to the power x, you still get e to the power s back. How many times you differentiate it doesn't matter. If I differentiate this 20 times, I'll still get e to the power s back. Okay. So hence the differential of e to the power s is always e to the power x. Okay. Now differentiate e to the power negative 2s plus 1. Okay. You go through step by step like we know. Ln of y equals ln of this, and this will give me what? Ln of y equals, from logarithm I can bring this in front, it becomes negative 2s plus 1 ln e. Now I differentiate both sides implicitly. I get 1 over y times dy dx equals, the differential of this side will give me negative 2 ln e, and this implies that I have dy dx equals what? Y negative 2y ln e. And like I said, ln e is always 1, so we become negative 2 e to the power 2x minus 2x plus 1. So it means that when I have e to the power u of x, then the differential of that will give me what? The differential of, I wrote it here. Okay, so if I have e to the power u of x, then the differential is always like the differential of the top, that is the u of x, times the same e to the power u. I hope this is clear, right? So this function doesn't matter whatever that is at the top, always will repeat itself in the differential and multiply by the differential of the top. So if you can remember this one, it means u of x equals what? X. The differential of this will give me what? 1. So it becomes 1 times e to the power x. Okay, same thing applies here. Okay, so let's look at this. Differentiate e to the power 3x into bracket sine x plus cos s. How do I differentiate this? All right, okay, so this is how you go about it. The differential of this, you use product rule, since there is a function of x multiplying other functions of x. Okay, so use product rule, hence we keep this one, then you differentiate this side. The differential of the, what do we say? We say that the differential of this is always differentiating the top and multiply by the same thing here. So if I differentiate the top one, 3x, I'll get what? 3 times e to the power 3x. And I keep this side, sine s plus cos s. Then plus, keeping this and differentiating this, e to the power 3s. Differentiate sine x, you get what? Cos s. When you differentiate cos s, you get minus sine s. Now I can multiply through and try to simplify. Okay, so if I multiply through by 3 of this one, I'll get 3 sine x plus 3 cos s. Then I factor e to the power 3x out. Okay, so in the first place, you can do the factorization first and you get e to the power 3x, and here will be left with 3 times the whole of this plus this one, and 3 times the whole of this will give me what? 3 times sine x plus cos s will give me 3 sine s plus 3 cos s, and plus cos s minus sine s. Now if I do some simplification here, I'll get e to the power 3x, then into bracket 3 sine s minus 1 sine s is what? 2 sine x. Then 3 cos s plus 1 cos s is what? 4 cos s. So that will be the derivative for it. And that is it. Looking at this, there is a 2 here, there is a 2 here that I can factor 2 e to the power 3s out. I'll get what? sine x here plus 2 cos s. Okay, so thank you for watching the video, and then subscribe to my channel if you haven't yet. Share and like for more video. Okay, see you next time.